Good morning, everyone. Today we will see optimal binary search tree. We can store elements in a binary tree. The elements can be searched efficiently with minimum cost using optimal binary search tree. Optimal means that search time is reduced in binary search tree. It is called optimal binary search tree. Then, what is tree? What is binary tree? What is optimal binary search tree? We will discuss some key terms. First one, tree. We know tree is a hierarchical structure with elements. It has a parent-child relationship. The topmost node is called root. Root has child node. Again, child can act as a parent. It has child node. Then the last level in the tree is called leaf node. The last level in the node in the tree. That means it has only parent, no child node. That is called leaf node. And the topmost node is called root node. That is called tree. Tree is a hierarchical structure with parent-child relationship. What is a binary tree? Each node has at most two children. Some node can have zero children. That means can be a leaf node or it can have one child node or it can have at most two children. That is called binary tree. Each node can have at most two children. That is binary tree. Search tree. The tree we are searching for some elements, key values in the tree. The tree is used for increasing the efficiency of searching process. That means speed will be increased. The searching cost is reduced. Binary search tree means it has the property or there is a node left, root and right. Root value is greater than left child and right is greater than both left and root. That is the property of binary search tree. Then what is optimal binary search tree? If you are searching particular element, the searching cost is minimized, minimizing the average search time based on the probability value. That is called optimal binary search tree. For example, take keys 10, 20, 30, 40, 50, 60. So the root is 40. All the values the left side of root is less than 40. All values in the right side of root node, that is 40, greater than 40. So this is a property of binary search tree. Then we will see how to implement optimal binary search tree. So OPST is a classical application of dynamic programming. We know what is dynamic programming. There are two approaches, top-down and bottom-up. There's memorization and tabulation. Here, we are solving the problem, sub-problem. The results are stored in a table that can be reused for finding the next solution to the overall problem. See, particularly here we have number of key values. Each key is assigned with probability. There are two types of probability, probability for success and probability for failure. And if we know in advance how frequently each key is accessed, how often the key is accessed, that will have more probability. If the key is not accessed often, that has the probability less value. So that is called input. You want to arrange the keys in a tree to minimize the average searching cost. So based on the probability of search key value, we have to construct an optimal binary search tree to reduce the searching cost. And so we are making the tree balanced to reduce the searching cost. And given a sorted array of n distinct keys. So we have key values. N is number of keys. N represents number of elements. That is n. We are sorting in ascending order. And we have two probability sets. That is probability for searching for keys k1 to kn. So each key has the probability for success searching keys. And q is 0 to n, the probability of searching for dummy keys. The key is not present. That is unsuccessful search probability. between and outside the actual keys. So first one is P is the probability for success. Q is probability for unsuccess search. That means unsuccess means the key is not present in the tree. Here we are going to build a binary search tree with minimum search cost. That is optimal binary search tree. Optimal means we are going to develop a binary search tree with minimum search cost. That is optimal binary search tree. What's a cost function? Cost of binary search tree is cost of I equal to 1 to n. N is number of keys. PA is the probability for each keys. And depth is the number of levels in the tree. For the root node, the depth is 1. The next level 1. That is the number of edges from the root to the current node will be considered. That is called as depth. So depth of Ki. And j is equal to 0 to n. Qj of depth. Q is the unsuccessful probability. Q of j, depth of dj, where depth of x is level of node x in the tree. The depth means the level, node level. The root node has 1, the next level 2, like that. We have to find out the depth of each node in the binary tree by adding total probability for success and unsuccess. We can get the cost function. These functions should be minimized. And so we will see general approach for solving optimal binary search tree using dynamic programming. So we are using 3 tables here. E of I comma j, W of I comma j, and root of I comma j. And what is E of I comma j? It's a minimum cost for searching k, particular key in a binary search tree. That is a minimum cost. And Wi of j, sum of probabilities from pi to pj and qi minus 1 to kj. So W is the sum of probability for success and unsuccessful search. And root table stores the possible root node for constructing binary search tree. So in this problem, we are going to derive values for 3 tables. First one cost table, second one weight table, third one root table. Initially, step 1, initialize the tables for length equal to 0. This is an empty tree. So all E of I comma I1 is Q of I comma 1 and W of I comma I minus 1 is Q of I comma 1. That is initial values. The probability given in the problem are taken and compute in increasing order of subtree length. So initially the tree is empty and we are going to develop a construct a tree for length I equal to 1 to n. And for each pair I and j, so the I plus j value changes from I plus 1 to minus 1. Initialize E of I, initialize the diagonal value, other values are infinity. And compute W, weight of node I and j. So I and j is pair. So so we are adding. How we are calculating W of I comma j minus 1. And we know the probability for success P and probability for failure Q. Add this value, we can compute W of ij. After computing W of ij, we are trying the possibilities from for each k from I to j as a root. So we have the range from I to j. We are choosing each node from I to j as a key node, root node. So which root node k gives minimum cost, that will be taken as the root node. So that should minimize the cost. E of ij is a cost. So which k gives the minimum cost from I to j, that will be taken as the root node. And we will see one example. There are 3 keys, n equal to 3, 10, 20, 30. There are 3 keys and probability is given. The probability for success 0.3, 0.2, 0.5. For unsuccessful probability, Q is if the key is not present, what's the probability? Unsuccessful probability. So now we are going to construct optimal binary search tree. So here K is given, P successful probability is given, and Q unsuccessful probability is given. Now, before 10, between 10 to 20, 20 to 30, and after 30. So we are going to build three tables: cost table, weight table, and root table using the dynamic programming strategy. First, initially step 1, cost table, weight table, and root table. So that values are going to fill from the key I to J, expected search cost from I to J, and weight, sum of probabilities from I to J, and root of I comma J. This is which node can act as a root from I to J. That is the table. See the example. Initially, initially the tree is empty, empty trees, just a dummy keys. Just add a dummy keys 0.1, 0.1, 0.1, and W also 0.1. And now we are going to find out root node for single key. For single key, that is E of 1, comma 1, E of 2, comma 2, E of 3, comma 3, which will be the root node. So find out W value weight, W1, comma 1. So add all these values, W, apply the formula W of 1, comma 0, P1, Q1. Add the value, W value is 0.5 and the cost value is 0.7. Now, initially we are taking root of 1, comma is 1. So there's only one node, the root node will be 1. For 2 also the root node will be 2. For 3 also root node will be 3. For single node, the same node as root node. And go to step 3. We are taking length 2. We are taking 2 keys. First 2 keys, 10, 20, then 20, 30. So we are taking every 2 keys, which will be the root node. So that is the range. E of 1, comma 2 means from 1 to 2. That is from first to 1 and 2. First, we are taking root node is 1. What will be the cost? That is 1.5. And try root node with 2. That is 20 is the root node, 10 is a child node. What will be the cost? See, we have values 1.5 and 1.6. So 1.5 is the minimum cost. So root node 1 gives the minimum cost for searching a key. So minimum is 1.5. The root node is 1. So the cost will be the minimum cost. Among 1.5, 1.6, 1.5 is the minimum. So which root gives the minimum? Root 1. So that is the value stored in a root table. Root 1, comma 2 is 1. Next, we are taking another option 2, comma 3. We are taking next to 2 and 3, that is 20 and 30. So we find the W value by using the formula, and we are going to try root node is 2. Assign root node is 2, find out the cost value. Then assign root node is 3, find out the cost value. So which is minimum? 2.0, 1.7. So 1.7 is minimum. So that can be, the root can be chosen as the root, assign as the root node. That is root 3. So minimum cost is 1.7 with the root E. So update the value in the dynamic programming table, cost table, and root table. E of 2, comma 3 is 1.7. Root of 2, comma 3 is 2. Next step, we are taking all the keys. 1, 2, 3. 3 keys. We are finding which is the root node. So find out W value. W of 1, comma 3 is 1, comma 2, P of 3 plus Q of 3, that is 1.4. That is fixed for all the combinations. Now we are going to try if 10 is the root node, what will be the cost? That is 3.2. 3.2. If root node is 1, the cost is 3.2. If root node is 2, the cost is 3.0. If root node is 3, the cost is 3.0. So which root gives minimum value? 3.2, 3.0, 3.0. So two values are minimum. So we can take either 2 or 3 as root node because it's a tie. So minimum is 3.0, the root node 2, comma 3. Now E of 1, comma 3 is 3.0. So root among node 1, 2, 3, root 2 or 3 can act as a root node. Now, expected cost E table is, this is 1. So all diagonal value keys, the probability 0.1, and for 1, 1, 0.7 is the minimum. The corresponding root value 1 gives the minimum value, and 0.6, 0.9. Then for every two nodes, that is 1, 2 and 2, 3. And next one is 1, 2, 4, 3.0. The corresponding root value, which root gives minimum cost, that will be stored in a root table. The cost is stored in a cost table. This is the final result. Now, we are going to construct a binary search tree. So, what is given here among 1, 2? That means first two keys, one is a root node. What's the first two keys? 10 and 20. So 10 and 20, among 10 and 20, 2 is the root node. That is 20 is the root node. So 20 is root means 10 is by default the left child of the root node, because it has the binary search tree property. Root is always greater than left child. So among 10 and 20, 20 is the root node. By default, 10 will act as a left child of the root node 20. And root of 3, see, root of 2, 3. 2, 3 is 20 and 30. 30 is the root node. So see, 20 and 30, 20 is the root node. So by default, 30 will be the right child of 20. So like that, we have to construct a tree. Using the root table, we have to construct the tree. So take two nodes, which is the root node, that will have to be the root. And check another value. If it is less than root, that will be the left child. Another one, if it is greater than root, that will be the right child. So this is the final optimal binary search tree. So final, the minimum cost is 3.0. So the root is 20, left is 10, the right is 30. This is an example for generating optimal binary search tree. So in the generally, we are taking first iteration, we are assigning all the values, cost value in a table, weight value and the root value. And for a single node, the same node is a root node. For two nodes, we are taking every two nodes, 1, 2, 2, 3. Every two nodes, finding which is the root node with minimum cost. Then the next step, take every three nodes, 1, 2, 3, and if you have more than three nodes, next remaining 2, 3, 4. So find out which is the root node. That minimum cost is stored in a table E, and which node gives the minimum cost, that will act as a root node, that will be stored in a root table. So from the root table, we have to generate a optimal binary search tree. And this is a Python code for finding optimal binary search tree. Initially, we are having three tables: E table, cost table, weight table, and a root table. So this is there's no recursive call, bottom-up approach. It's a tabulation method. It uses all the values are stored in a table that can be reused in a next subsequent process. So we are solving from base case to problem case. So it is based on dynamic programming based on iteration method, bottom-up approach, tabulation method. So we are using for loop for I in range 1 to n plus 2. Find out the probability value. E of I comma I minus 1 is Q of I comma 1. So for I in range 1 to n plus 1, for I in range, that is 1 comma n minus 1 plus 2. So we are taking every two nodes, length 1, length 2, length 3. We are finding the cost for each pair, and which root gives the minimum cost, that will act as a root node. And so this is the time complexity. N is number of keys in a tree. So we are using three for loops. 1, 2, 3. Out three for loops we are using normally. So that is time complexity is order of n cubic, and space complexity order of n square. We are using table, two-dimensional table. So two-dimensional means n into n square. So the space complexity is n square, because it use all dynamic table use two-dimensional 2D table, rows and columns, though n square. And time complexity is based on the number of iterations, number of looping statement. Here we are using 3 looping statement in the Python code. So time complexity will be order of n cube. and applications where we can use 0, 1, that is optimal binary search tree. So mainly it's used for compiler design, database query optimization, decision trees, and autocomplete systems with search frequency. Thank you.